Hi folks, and welcome back. Today we begin chapter 11, which is the last chapter in our course. It has only 3 sections, so we are very near the end of our work. We're going to review a little bit of work on parametric equations in section 11.1. And remember just how we graph them and what graphs look like and what we can do with them. So let's begin with an example. So here's a typical parametric set of equations. We have t from 0 to 2 pi, x is equal to 3 times the cos of t, y is equal to 2 times the sine of t. T is our parameter. And let's see if we can pull in what a graph looks like. So here you see what the graph looks like. And if we do a little manipulation on our set of parametric equations, one of the things that we'll discover is that we have this equation, which is x over 3 squared plus y over 2 squared is equal to cos squared plus sine squared, which is 1. And so that gives us the equation which very much looks like like an ellipse. Center is 0, 0. We go 3 each way on the x direction and 2 each way in the y direction. So we've talked about how we graph these. We can graph them by hand. We can graph them on our calculator. And here's another example. So here we have x being the square root of t, y being t minus 2, and we're letting t range from 0 to 4, and it looks like we're getting a parabola. And it's pretty easy to see how we could manipulate this. If x is equal to the square root of t, that means t is equal to x squared. So actually y is equal to x squared minus 2, and that's exactly the way this graph over here looks. So graphing is not a big deal, something we've done before. We've actually taken some derivatives before, but we want to just try to standardize all of the work that we have done with parametric equations. So, as you've seen in these last 2 examples, when we graph parametric equations, they often turn out to be smooth graphs. They might be a relation, might be a function, but they tend to be smooth. And since they're smooth, we are able to find dy dx. When we graph them, we're graphing them in the xy plane, and so t sort of disappears in that case. So suppose we want dy dx when we're given x is equal to, let's say x is equal to f of t and y is equal to g of t, and we want dy dx. Well, it's really quite simple. Dy dx is simply dy dt over dx dt. And when we do that, we'll get an expression that involves t. So let's look at an example of this. Okay, so let's take a look at this example where we have x and y defined as you see. T is between 0 and pi. We don't really care what the graph of this looks like right now. So if we want to find dy dx, well, that's simply going to be dy dt over dx dt. Dy dt is 2 cos of t over dx dt is 2t, and so what we get is simply cos of t over t. And notice that our derivative of y with respect to x is in terms of t. And maybe we could eliminate the t's and maybe we can't. But what this does is tells us what the derivative is, what the slope of the tangent line is at any particular value of t on the curve. And so the interesting and challenging question is, once we have found dy dx, what exactly do we do to find the second derivative of y with respect to x? It's not, as most students would guess, just the derivative of this. And we'll see why on the next page. So let's pick up where we just were. We found that dy dx for this set of parametric equations is cos of t over t. And we want to now find the second derivative with respect to x. Well, what that means is the derivative with respect to x of the first derivative of y with respect to x. And that's the key, to think of it and write it like that. So in a similar way, we see that we can write this as the derivative with respect to t of y prime over the derivative of x with respect to t. And that's really the trick right there. So let's see how it works on here. So the first thing I'm going to do is take the derivative of y prime right here with respect to t. And when I do that, I have to use the quotient rule. So it's going to be low d high minus high d low all over low squared. So that gives me the top part. For the bottom part, I need dx dt. Well, we've already computed that, right? Dx dt is just 2t. And so if we simplify this a little bit, I'll have to save a little room here. Let me change my color. If we simplify this, what we get is minus t sine of t minus the cos of t all over 2t cubed. And that is the second derivative of y with respect to x. So it takes a little bit more work. You got to keep your wits about you, and you got to follow this little formula right here. Okay? Okay, so now let's take a look at how we compute the arc length of a curve defined parametrically. If you remember, we've done this already with functions of a single variable, but arc length with a parametric curve is a little bit different, although we set it up exactly the same. So let's suppose we have some curve, and we're looking for the length of that curve, and we break it up into a partition. And let's suppose that what we're going to do is approximate the length along the curve with the length of the secant segment. And this should be a familiar picture to you all. This is a little delta x, and this is a little delta y, and we call this distance here delta s. So what we know is that the length, the actual length, is going to be the sum of all of these delta s's for each kth subinterval, and the exact length is what we get when we let n, the number of subintervals, go to infinity. So that picture should be familiar. Also, you should be able to recognize that delta s in any one of these cases is just a square root of delta x squared plus delta y squared. So here we're starting exactly the way we started with a function of one variable. It's what happens after this that becomes a little bit more interesting. So any one of these little delta s's corresponding to the length of a secant segment is equal to the square root of delta x squared plus delta y squared. And now here's where we change things up a little bit in the parametric world. We're going to do this. We're going to write this as delta x over delta t squared plus delta y over delta t squared. Now to balance those delta t's, I multiply outside the radical by delta t. Now, as n goes to infinity, this is going to go to dx dt, and this is going to go to dy dt, and this is going to go to dt, and so we get the formula that the length is equal to the integral from the beginning point to the end point of the square root of dx dt squared plus dy dt squared dt. Similar, but not exactly the same as what we had when we were just looking at dy dx. Okay, so let's just finish this off with an example. So here's a simple example that we can look at. And so we have an ellipse defined by these parametric equations. As t goes through one full revolution of the unit circle, and we want to find the circumference of that ellipse. So therefore, that circumference, or length, will be the integral from 0 to 2 pi of the square root of dx dt, which is cos squared, plus dy dt squared, which will give us 9 sine squared of t, dt. And just as in previous problems, most of these lengths, arc length, unless they are fairly contrived, require you to use your CAS tool, your Inspire, or your TI-89 if you haven't made the adjustment yet. And if we use a CAS, we should learn that this length, this circumference, is 13.3649. And so there we go. And that takes care of the first section in Chapter 11. 2 to go. See you later. Ciao, ciao.